The universe is big. Now let's take a tour of it using the speed of light as our guide. Light travels around the Earth 7.5 times a second, 300,000 kilometers per second. And so that means when Neil Armstrong took his small step, we found out about it 1.5 seconds after it occurred. Now, you may not realize it, but the sun is much bigger than the Earth-Moon system, about 5 light seconds across. But it appears so small because it's so far away, 8 light minutes in distance. Now, when you leave TEDx this evening, I want you to look up in the sky, and I want you to look at the brighter of the 2 pointer stars to the Southern Cross, almost straight overhead. That stellar system, Alpha Centauri, is the nearest star to us, 4.3 light years in distance. So if you think Alpha Centauri being a P, and it turns out Alpha Centauri is much like our own sun, another P, and I'm standing here in Sydney as Alpha Centauri, the sun would be located 270 kilometers down the road at my vineyard just outside of Canberra, with all that space empty between us. And that's particularly remarkable when you think that we are one of the most exciting places in the universe, a galaxy of 100 billion suns, and we're located some 30,000 light years out from the center of our own Milky Way. Now, the Milky Way is just one but of many galaxies. The nearest galaxy of any size is the Andromeda galaxy, visible in the northern hemisphere, 2 million light years in distance. Now, we astronomers like big telescopes so we can see a long ways into the universe's past. The deepest picture we've been able to take of stars and galaxies is this one, taken with the Hubble Space Telescope. It looks back 12 billion years into the universe's past. Each one of those dots is a galaxy with tens and hundreds of billions of stars like our own Milky Way. This image is 1/32 millionth of the sky. So while the universe is big, the part that we can see is not infinite. And that is because we simply run out of time. Here is an image of the universe 13.7 billion years ago. You're not seeing stars, you're not seeing galaxies. You're seeing a sea of hydrogen and helium formed at the very beginning, the Big Bang. All right, so if we go out and look at how we figured all this out, it really all started at the beginning of the 20th century. If you take the light of a star and you spread it out into the colors of the rainbow after looking at it with the telescope, you will see that every element has a fingerprint of color which it emits or absorbs. And that fingerprint allows us to see what's going on in the distant universe. A man most of you have not heard of, Vesto Melvin Slipher, took the light of galaxies and spread them out into these spectra, as we call them. And he saw that these galaxies looked a lot like stars, but there was a difference. Their light was stretched to the red. And he could understand that using something called the Doppler shift. Now, the Doppler shift we're familiar with here on Earth because it affects sound waves. So, for example, if a police car is coming towards you, its siren sounds are compressed. And when you compress sound, it raises the pitch. As the car goes away from you, then we see it from the other side. We see the sound waves lengthened or lowered in pitch. Now, light is a wave, just like sound, and so the same thing occurs. If a galaxy is moving towards you, its light is compressed, making the light bluer. If it is going away from you, the light is stretched, making it redder. So in 1916, when Slipher made these measurements, he found something remarkable. He found that almost every one of these galaxies was moving away from us, indicating we were something seemingly very special in the universe, a place which everything was rapidly trying to get away from. Now, that was a mystery that was solved by measuring distances. We astronomers cannot just go down and lay a ruler down between us and the nearest galaxy. We have to do things by how things appear. So, as you go further and further away, things appear fainter or smaller. And Edwin Hubble was able to use this fact in 1929, thanks to having access to the largest telescope in the world at the time, the 100-inch Hooker telescope just outside of Los Angeles. And he went through and he looked at stars in Slipher's galaxies. and he judged their distance by how bright those stars appeared. And what he found was that the faster the galaxy was moving away, the fainter its stars. Or in other words, the further the object was, the faster it was moving away. And he proclaimed that that meant, in 1929, that the universe is expanding. Now, why did he say that? Thanks to the wonders of a computer, I'm going to make a little toy version of the universe, which I will expand for you. And now I want to take those two images and I want to overlay them. And what do I see? I see from our vantage point of an expanding universe that nearby objects have moved a little bit and distant objects have moved a lot. In other words, in an expanding universe, we see that the further away something is, the faster it will be moving away from us, just like what Hubble saw. Now, we also understand the expansion of the universe because of Albert Einstein. Albert Einstein's theory of gravity was born out of a thought he had in 1907. And that thought was that he felt that acceleration due to motion was equivalent to acceleration due to gravity. That is, if you were in a box here on Earth, or in a box in a rocket that was accelerating, you cannot tell those two situations apart. A small thought, but one that took Einstein more than 8 years to figure out. And in the end, it was his equations of general relativity that were the result. They predicted curved space, and it also allowed him to do something that Newton was never able to do with his version of gravity, which was to solve for cosmology, how the universe works on large scales. But there was a problem in 1917 when he did this work. His solution said that the universe should be in motion. But this was 12 years before Hubble made his discovery that the universe was expanding. So he had to think and look at his equations very carefully, and he realized he could do something. He could add something he called the cosmological constant. This is energy that is fundamental to space itself, and this stuff makes gravity push rather than pull in his equations. So by adding a bit of this stuff into space, he could counteract the effects of gravity and make the universe stable. Well, it turns out it doesn't work for a variety of reasons, but especially in 1929 when it was realized that the universe actually was in motion. He later described this as his greatest blunder, not predicting that the universe should be expanding. So imagine a universe which is expanding. Well, of course, as it gets, we run it in reverse, things get closer and closer and closer, and you naturally come to the idea of a Big Bang. That is, you have the time when everything in the universe is on top of everything else. So, if we run the universe in reverse, you will see things get closer and closer and closer, and they come together. Graphically, if we look through two objects separated in time by a certain distance, you can run the universe in backwards. So the steepness of this line is how fast the universe is expanding. We call it Hubble's constant. And so knowing how fast the universe is expanding tells us when the Big Bang happened, how old the universe is. But there's one other thing we need to worry about, which is that the universe is full of gravity. And gravity will slow the universe down, just like the gravity of Earth will slow down a ball that I throw up in the air. And so the trajectory of the universe will be different if there's a lot of gravity in it. It will be expanding faster in the past and slow down. Now this has ramifications for what we can expect the universe to do in the future. Imagine a universe which isn't slowing down. It gets bigger and bigger and bigger forever and ever and ever. It's a universe that's infinite in time. On the other hand, a universe which is slowing down will eventually, if it's slowing down enough, reach a maximum size. And just like the ball I throw up in the air here, it will start coming back down to Earth. The universe will go into reverse and start to collapse. And so, while both universes start in a Big Bang, that second universe will, of course, end in what we call a Gnab-Gib. That's the Big Bang backwards. All right, so the slowing down of the universe affects how old we think the universe is from the Hubble constant. It tells us the ultimate fate of the universe, and it also tells us the shape and weight of the universe. So a heavy universe literally wraps onto itself. It is finite. A light universe wraps away from itself and is infinite. And then there's that just right universe. universe, the universe precariously balanced between the finite and the infinite. So when I moved to Australia in 1994, I decided I wanted to do something big, and measuring the ultimate fate of the universe was the biggest thing I could think of. And so the idea is to literally look into the universe's past and recreate Hubble's experiment by looking far, far away, and therefore into the universe's distant past. Imagine a universe which is not slowing down. It's expanding the same in the past as now. Well, that universe is empty and infinite. On the other hand, a universe which is slowing down on this trajectory, gravity wins, the universe is heavy and finite. The other side of that line, it's infinite. So how are we going to do this? We're going to use type 1a supernovae, nature's gift to astronomy. Exploding stars 5 billion times brighter than our sun. These objects are almost all the same and allow us to measure distances very precisely. They also synthesize 2/3 of the iron in this room. And so two teams, one called the Supernova Cosmology Project, and another one called the High Redshift Supernova Team, shown in our traditional astronomical gear here of tails and white tie, went through and made these measurements back in 1998. And what we found was quite remarkable. In this diagram, I show you each exploding star and the distance we measure. Now, the distances have uncertainty represented by the bars. And so if you look at the nearby objects, well, they don't really tell you what's going on. On average, they line up with all parts of the diagram. But these distant ones are clearly not a single one is consistent with the universe that's going to slow down and go in reverse. But they're also, on average, not even in the yellow part of the diagram, the part of the diagram that says that the universe is slowing down. Rather, they're in the top part of the diagram, the part of the diagram that says that the universe is actually speeding up. So what would be causing the universe to speed up? Well, we only have to look to Einstein, to that thing, the cosmological constant he invented. Energy as part of space fits the bill. And we generically call that stuff dark energy now. So, needless to say, if you go through and look at our results, we can go through and do a detailed analysis, and we find that in order to understand these exploding stars we see, we need a universe that's 30% stuff that pulls and 70% of stuff that pushes. So here in Australia, people wanted to go through and check this result out, so the first thing they decided to do was to weigh the universe. So here's a map of 221,000 galaxies where they can measure the motions of the galaxies and weigh the universe. And when they do that experiment, they find out that the universe has enough gravity that it's attracting to account for 27% of the amount of stuff necessary to make the universe flat, to bend the universe. So the other mystery is that if you go through and try to figure out how much stuff there is in the universe, that's 5 times more gravity than we can account for from the atoms that we see in the universe. So that brings up the idea of dark matter, the stuff whose gravity we can infer, but which we cannot see. Now, the other experiment came from this picture of the early universe, the cosmic microwave background. Here we see a sea of sound waves that are rippling through the universe, and physics here on Earth that we understand very well tells us that these light waves are 430,000 light years long, very precisely. And so these are our ruler, which we can judge distances very precisely in the early universe. Now, the size of a ruler depends, it turns out, on the shape of space. Just like things in your rearview mirror, objects appear larger in curved finite space. And so by looking at the size of those sound waves, we can judge the geometry of space. And the answer we find is that the universe appears flat to 1%. Now, any type of matter contributes to this, and so if we do a little bit of cosmic subtraction, we find that 100% of everything contains in that geometrical information. 27% of the universe is this stuff that's attractive, leaving us with 73% mystery matter, the same stuff that appears to be pushing the universe apart. So where does this leave us? It leaves us with a bit of a mess, where 4.5% of the universe is stuff we can see, and the rest is this dark matter which pulls and dark energy which pushes. So what's the future of the universe? Well, the future of the universe seems to be dark energy. The more space expands, the more dark energy can push against gravity, creating even more space and even more dark energy. Eventually, the creation of space happens even more quickly than light can travel. And so light from the galaxies we can see today will literally get stranded on its way between us and them. But until we understand what's accelerating the cosmos, anything is possible. And so, unless dark energy suddenly disappears, the universe will, at an ever-increasing rate, expand, fade away, and leave cosmologists of the future with nothing to say.